come and present today. So, yeah, this is actually work for me started a long time ago. I was interested in the problem of how you would actually implement decoding algorithms in hardware. And then later on, it turned out that machine learning became a hot topic and that I was already using these topics in machine learning. So that gave me the right to put the phrase machine learning in the title. Okay, so we use lots of communication receivers. So just your smartphone alone has numerous communication receivers, you know, the one for cellular radio, for Wi-Fi, Bluetooth, but your cell phone also has flash memory, which has an error correcting code in it. So we can think of this as being a receiver as well. And of course, besides your smartphone, there's many other possible applications, you know, digital video broadcast, wired Ethernet, SSDs, and so on. There's many, many communication receivers. But I mean, probably all of us implement algorithms that do some sort of communications, but usually we just run at our computer and the computer uses floating point. But many algorithms actually need to be implemented in hardware. Why? Well, because they're more efficient than CPUs is the main reason, and it's cheaper to implement and they're fast. But so they're implemented in VLSI. It uses integer arithmetic or fixed point arithmetic. Floating point is, generally speaking, not available. And so the question is, how do we implement algorithms in VLSI? So certainly, when you approximate real numbers using integers, there's going to be a trade-off. So if you have more bits per integer, you'll get better performance, or at least the performance will be close to floating point. But if you have fewer bits per integer, then you'll have more efficient VLSI because those bits actually take up space in the chip. Not only in terms of storage, but also in terms of just moving the signal around on the chip. So engineers often implement quantization schemes in some sort of an ad hoc fashion. So, they got the algorithm from people like us, and then they have to actually put it into the chip. And, they have to convert to fixed point numbers, and essentially they try different quantization schemes, and they just choose the best one. It's very ad hoc. So fundamental question is, can we give a theoretical foundation to this quantization operation in communication receivers? So when I say communication receiver, I mean equalization and detection, but really most of them talking about error correcting, particularly the LDPC codes. So in this talk, I'm going to basically be talking about implementation of LDPC codes. Okay, so this is the outline of the talk. I've got three parts. The first part is a background on communication and LDPC codes, just to let you know what I'm talking about. And then the second part is quantization and classification. I'm going to make small connections between machine learning and information theory as it's needed to do what I need to do. We'll talk about, and then I'm going to talk about the problem of quantization of discrete memoryless channels. So this is a basic problem that we need to solve. So first case is when we have a channel with binary inputs, we can do this optimally. And then we have the case where the inputs are non-binary. And then finally, we'll take those two parts and combine them in section 3, and I'll talk about hardware-aware information theory. There's a technique I call the Max-Let method, which is a way of implementing the decoders using a finite number of bits. And the punchline, the main result, is that this works amazingly well. So it's efficient and it gives good performance. And what we found numerically is that for LDPC decoding, using 4 bits per message, we can get performance similar to floating point. Okay, so maybe everybody knows this already, but we'll point it out. We want to communicate over a noisy channel. We have an encoder, and we have k bits of information that is encoded to an n-bit code word. This is transmitted over a noisy channel. The received sequence is y, and the decoder's job is to estimate either the code word or the transmitted data. So the code rate, of course, is k on n, And we already know that if the channel is good, that is, the channel has high SNR, then we can use a high code rate with only a few parity bits. And if the channel is bad, we have to use a low code rate with many parity bits. So how high can this rate be? We want it to be as high as possible. Well, of course, Shannon told us that the code rate can be no larger than the channel capacity. And the channel capacity is, of course, the maximization of mutual information. And Shannon has something to say. Right. So mutual information is the highest achievable rate. Okay, so we're all familiar with this, but I'm bringing this up because later we're going to need to have some metric. And we could choose many different metrics, but because we're dealing with communication systems, I think it's very natural to choose maximization of mutual information as a metric. Okay, and then I want to just remind you about why LDPC codes are so important and interesting. They're now widely used error correcting codes. So it seems that almost any new communication system the standard includes LDPC codes. So 5G and presumably 6G cellular data uses LDPC codes. All of the recent Wi-Fi standards use LDPC codes. One of the first standards to use LDPC codes was video broadcasting, also wired Ethernet, and now it's widely used in flash memories and SSD drives. So why are LDPC codes used so much? One is that they're just good codes. So long codes get very close to the Shannon limit, at least empirically. And besides being good codes, they're efficient to decode. So the complexity, roughly speaking, is linear in the block length. So these two facts together make them very attractive. Okay, and so I feel like you guys know this already, and so I'm embarrassed to tell you this, but I'll go ahead with this slide anyway. So an LDPC code is defined by a parity check matrix, H, with low density, and a code word, X is a code word if the parity check matrix times X is equal to 0 modulo 2. So here's a simple example. We have a parity check matrix H here, which is sparse. And on the right-hand side is the Tanner graph, where the variable nodes correspond to columns of the graph of the matrix, and the square nodes or check nodes that correspond to the rows, and they're connected if there's a 1 in the graph. So we like the Tanner graph because it's a nice way to describe decoding. So very, very briefly, this is how decoding works. We receive messages from the channel, and these are inputs to the input to the graph. The messages are passed up to the check node, and the check node performs some processing, and then the messages are passed back down, and the variable nodes perform some processing, and this iterates 5 to 50 times. And then we stop if the code word is detected or if a maximum number of iterations has been reached. Okay, so this is the perspective I need for this talk, which is that the nodes are functions and the edges have messages. So for example, at the check node, we have some incoming messages and we compute some function. The tanh function in this case is used to compute the outgoing message. Using all of the other incoming messages. That's the so-called sum product rule. And at the variable node, we take the sum of all of the incoming messages, except for the message on E. And so actually, it's not terribly important what these functions are, except to know that when an engineer wants to implement them in VLSI, he would need to know them. But what I'm going to show you is actually we just ignore these altogether. Okay, so here's our friend the engineer. How is he going to implement this? So for example, he might represent the messages using 2's complement arithmetic. It's specific mapping from values to bits. And then at the variable node, for example, you have to perform addition. At the variable node, you perform addition, and this is very well understood. So when I said it was ad hoc, what I meant is that, this shows steps of, it shows 3 bits and steps of 0.25. Why wouldn't you choose, steps of 0.5 and 4 or 5 bits? There's many possible choices. If you use about 7 bits per message when implementing the LDPC decoder, you get very similar to floating point performance with this type of quantization scheme. But 7 bits per message is too much. So you talk to guys in industry and you ask them, how many bits per message are you using in your implementation? And they say, that's a secret, I can't tell you. But probably they're using something around 3 to 5 bits per message. They're getting a small performance penalty. They have a small performance penalty in exchange of a little bit smaller, a little bit more efficient implementation. And then how do we implement nonlinear functions? The variable node happens to be sum, but if you want to implement the min function, if you're implementing the min version of the decoder, or if you actually wanted to implement the tanh, it's kind of very complicated to do this in fixed point arithmetic. So instead of these ad hoc schemes, can we consider a more theoretical approach? Okay, so we remember all of this. In the next section, I'm going to talk about information theory and machine learning, and then we'll combine the two. Okay, so in this section, I'm going to talk about quantization and classification. So the key problem that I need is channel quantization to maximize mutual information. But there's strong similarities with classification in machine learning. In fact, you could probably say these are almost the same problem in certain situations. And so for the quantization problem, I have an optimal polynomial time when the channel input is binary. And I'm going to introduce the k-means algorithm, which you probably have seen before. It's called the Lloyd-Max algorithm in information theory. And then we're going to use that to perform channel quantization. And that's going to give us something called the k-l-means algorithm. Okay, so here's a very simple classification problem as an example. We suppose X is a fruit. It's either a strawberry, a banana, or a kiwi. And we have a 1-pixel camera, which takes a picture of the fruit and provides some sample Y. So all we get is a color. And then this classifier has to choose which fruit it thinks was taken. So either a strawberry, banana, or kiwi is the output of the classifier. And so we can make this a little bit more formal in the sense that if we have some joint distribution between X and Y, and then given Y, we want to classify that into Z. And so in machine learning, there's many different objective functions. For classification, you could use Euclidean distance or log loss, but one of them is actually entropy minimization. And when you're in the machine learning field, Q would be called the classifier. But for the information theory approach, we want to maximize mutual information, but you can see from the basic definition that that's the same as minimizing entropy. And in this application, Q is going to be called a quantizer. And so I'll just point out, so obviously this looks like a discrete memoryless channel. That's on purpose because we like discrete memoryless channels. And then when I say quantization, I mean reducing a large number of outputs to a smaller number of Z, where they're both discrete. Usually when you say quantization, you think of continuous to discrete quantization. But when I say quantization, I mean discrete to discrete quantization. Okay, so here is the central problem that I want to solve. We have a well-defined mathematical problem. So given this discrete memoryless channel and its input distribution, so the joint distribution between on X and Y is known, we want to find this mapping Q, which maximizes the mutual information between X and Z, between the channel input and the output. And we're always going to have the alphabet of Z will be smaller than Y, because if they're the same size or larger, then the problem is is trivial. And then, as I mentioned earlier, because we're implementing quantization in a communication system, the choice of maximizing neutral information makes a lot of sense. Okay. So this is the one way of looking at the problem, which I think is helpful for understanding the why we can do this in an optimal way. So we start by using, I call it the backwards channel or the reverse channel. That's the probability of X given Y. The forward channel would be the probability of Y given X, yeah? And so then we can write that as a vector, U of Y. And in this example, I have three X values. And so that means this vector has 3 values. But since it's in a probability simplex, I can draw it in two dimensions and make nice pictures. Okay, so I have 6 outputs, and now I have drawn those 6 points in the probability simplex. And so what you would think then is then that points that are similar in the probability simplex should be quantized together. So can you see my pointer? For some reason, I have to do some magic to make my pointer appear. I just realized that there's people on Zoom. All right, my pointer's not appearing. Okay, anyway, the red and green points are next to each other, so those might be quantized together. And then those 3 dots in the middle, they're next to each other, so they would be quantized together. And this brown one down here is by itself, and it would not be quantized to anybody else. Okay. So now what I want to show here is that this is kind of a clustering idea. So now I have a channel with many more outputs, and now I have many more points in the probability simplex. And so each of the points which cluster together will map to the same output. So I've used colors to indicate similarity. So for example, all of the green points are in the same cluster, and they map to the same point Z. So the question is, how do you find these clusters? So what we do know, so there's several results. This one is from '92, but there's other results in the like early 2000s that dealt with finding these optimal clusters. And the preimage of cluster, or in the words of Bernstein et al., is that the preimage of the optimal quantizer is convex, which is to say that each of these clusters has to be convex. And so what we do, when we have a binary input, the probability simplex is now just this line from 1, 0 to 0, 1. And then we can take the outputs of our channel and write them on the, place them on the line. And then from this rule that the clusters have to be convex, that simply amounts to finding these boundaries between the clusters. And that can be done by a dynamic programming approach, and this is provably optimal. And so in this case, the complexity is m cubed. Okay. So what if the input is not binary? Well, in that case, we have to move to something else. And it turns out that the k-means algorithm, or the Lloyd-Max algorithm, is the tool that we need. And so the idea, of course, in classification is you have some points and you want to estimate and you want to classify the regions. So this is a picture from Wikipedia showing one iteration of k-means classification. But the idea is that we start with some initial choice of the k centers. And then for each one of those, we find the nearest neighbor. That is, the k clusters consist of data points closest to its mean in the Euclidean distance sense, right? So if you ever read this algorithm, they almost always start with Euclidean distance as the metric. And then once you've identified the clusters, then you move the centroid to the center of the cluster and then repeat this. So This iterates several times. This is not optimal, but it works really well in practice. And this is hugely successful in the field of machine learning. So I emphasize that the usual version is with Euclidean distance, but in the early 2000s, there was a lot of work on using other metrics, generalized metrics. And one of these papers got my attention, this one on text mining. So this was a paper in natural language processing, where they were, and they proposed using the k-means algorithm with the Kullback-Leibler divergence as a metric. So they called it the KL-means algorithm. Like, okay, that makes sense. That sounds sort of reasonable. I like that name, so I'll use the KL-means algorithm. So that's just this algorithm where I've replaced the Euclidean distance metric with the KL divergence. And that makes a lot of sense because the KL divergence measures the distance between two probability distributions, And we're working in a probability simplex. So this is some numerical results on just quantizing sort of arbitrary discrete memory list channels. I believe that this is the in the binary case so that we can compare with optimal. What we showed here was that maximization of mutual information is the same as minimizing the expected Kullback-Leibler divergence. Here, capital D is the Kullback-Leibler divergence. And so the numerical results show the trade-off. Let's see here. So the horizontal axis is the number of quantizer output, and the vertical axis is the mutual information loss. So the loss should be, ideally, would be as close to 0 as possible. So of course, as we increase that number of outputs, the number of, that loss is decreasing. And the optimal quantizer here is in green. And when the number of quantizer outputs is small, actually the KL means in blue does fairly well. And then there's a small performance loss when the number of outputs gets larger. The red curve is another technique called the greedy quantizer, or greedy combining. Okay. So the information bottleneck method was introduced in 2000, and that got a lot of attention. So the information bottleneck method by Tishby et al. Applies to the Markov chain, X to Y to Z. So that's exactly the same problem setup as we had before. So the question is, how much information Z provides about X through the bottleneck Y? And so the objective function is a little bit different here. So they are minimizing the mutual information between Y and Z minus beta times the mutual information between X and Z. But Tishby, they have a very nice optimization technique which solves this problem using the method of Lagrange multipliers. It's really quite a nice paper. I recommend you read it. But we're just interested in this case of maximizing the mutual information. So you can see that if beta goes to infinity, we get the same problem. So the question is the information bottleneck method the same or different from this KL means algorithm? And the answer is actually they're the same. So it turns out that in the special case of beta going to infinity, that the information bottleneck method is just k-means with a special metric. Okay, so now we come to the final section. So hardware information theory. So I talked about implement LDPC codes and how a designer might implement them. And I talked about how to do optimal quantization of discrete memory list channels. So now I'm going to bring them together in something I call the max-let method. So that's mutual information maximizing lookup tables. That's a term that unfortunately didn't catch on, but I think it describes the idea perfectly. And then we'll apply the max-let method to LDPC decoding And then I'll show you that the numerical results show that 4 bits per message performs like floating point. Okay, so how is it possible to replace the mathematical operations used in VLSI, like plus and tanh, with a lookup table? So maxlet is a method for implementing the node decoder functions in graph-based decoders using lookup tables that maximize mutual information. So the picture kind of illustrates the idea. You know, you might have some floating point numbers or something which is or it might be quantized. And then that could be implemented using labels. So 1, 2, and 3 just might be bits. But equally well, this could be placed into a lookup table. Okay, so what are the characteristics of the maxlet method? Well, we need a factor graph. We need input probability distributions. The messages are all discrete. And the decoding functions are assumed to be lookup tables. And we're going to choose those lookup tables designed to maximize mutual information. Okay. So here's an example of a lookup table. I've drawn sort of an arbitrary lookup table here. So we're going to assume that lookup tables are easy to implement in VLSI hardware. So this is sort of a basic thing that lookup tables can do. And we're not using quantized LLRs, we're just using labels. So we have this 0, 1, 2, and 3, which are just labels which can be represented by bits in an implementation. So if you stop for a moment, if you think about how you compute mutual information in a discrete memoryless channel, it doesn't matter what the labels on the input and output are, right? It doesn't matter that the inputs are 0 and 1. They could be 5 and 13, and it wouldn't change the computation of mutual information. In the same way, we don't care what the labels mean. They're just labels. Okay, so here's the central idea for factor graphs. And in order to explain this, I had to realize that there's actually 2 interpretations of a factor graph. So in one representation, it's the encoder side. So you could think of, for example, a check node, which is connected to x1, x2, and x3, and that's the function x1 plus x2 plus x3 is equal to 0. Or it could be a variable node, and in that case, the function is x1 is equal to x2 is equal to x3. So, but if you had some other factor graph that you wanted to quantize, you could have other, you could make other choices there. On the decoder side, the decoder perspective, we have the input L sub I. They're basically noisy versions of the corresponding X sub I. And the output Z, it's a noisy version of X3. So our goal is to find this lookup table, which maximizes the mutual information between X3 and its noisy representations. So what we want to do, essentially, is maximize over all possible lookup tables the mutual information between X3 and the lookup table output. So this comes in 3 steps. We need to find the joint distribution. We need to quantize it in order to maximize the mutual information, and then we construct the lookup table. All right, so in this example, I'll use a variable node with 2 inputs called L1 and L2, and the probability of L sub I given X sub I is known. The variable node has a local constraint, X1 is equal to X2, and the goal is to find the lookup table. Okay, so this is my favorite part. This is like really detailed, maybe a little bit too detailed, but this is sort of where the magic works. Like, wow, this works. So in this example, I have L1 has 6 levels and L2 has 4 levels. I just made that, I chose a strange number of levels so that would be clear. In general, they'd be the same and a power of 2. So we construct the product of these 2 distributions. So there's 24 outputs, and actually there should be 4 inputs to the product distribution. We have the local constraint, which says that x1 and x2 and x3 are equal. And so what that means is that we delete those inputs which are not, equal, don't satisfy the constraint. Okay, so we've got our joint distribution, and now we're going to quantize. We've got too many levels. So we've got 24 levels, and we just want to get this down to a smaller number of bits. And so we're going to quantize. So how do we do that? Well, we know how to do that. Well, we're going to maximize the mutual information between the input x3 and z, and we get some mapping using the technique that I showed you before. And so that gives us a quantizer Q. Now, how do you find a lookup table? Well, for all of these 24 outputs, they correspond pairwise to two of the original inputs, L1 and L2. And so for each of these mappings, we can fill in the table. So you can see the table has L1 by L2. And for example, our quantizer maps 5, 2 to the output 2. And so that means the entry in the table 5, 2 is 2. And we can do that for all of the values and get a lookup table. Okay. So that's the method. So how do we apply this to LDPC decoding? So we need probability distributions. How do we get those? We're going to do density evolution. And how do we keep the lookup tables to a reasonable size? All right, so there's a technique called node decomposition, or opening the node. So we just have these, if we had a check node of degree 6, naively, you would need a 5-dimensional lookup table. That's not practical. So what we do is we do a 2-input lookup table, one at a time. Okay. So density evolution unwraps the graph. So I'm cheating a little bit here because in density evolution, there's no graph, there's no graph structure, but it kind of illustrates what's going on. So we begin on the left side. And if you remember, we pass the messages up to the check nodes. And at this check node, we apply the max-let method. We construct the lookup table, and a byproduct is we also get the next density, probability of L given X. So then we pass that to the variable nodes, and we repeat the max-let method. We get a new lookup table and new distribution. And this just continues iteratively. A consequence of this is that we have a unique lookup table at each step of decoding. Okay, so I said the labels are just labels and they have no meaning, but we can do something since we have the probability distribution, is that we can go back and find the LLR values that each of those outputs had. So this is an example with 11 labels. And so when we go back and plot the LLR values, what you see is something that actually looks like non-uniform quantization. And it's relatively stable for most iterations, gradually increasing. This is because we're close to the noise threshold of this LDPC code. But then as we get close to convergence, then the levels change very dramatically. So what we're doing here, so one perspective is just to say, oh, we're doing non-uniform quantization where the quantization values change at each iteration. Okay, so here's the numerical results. So we did this one first with noise thresholds. This is for a 3/6 regular LDPC code. The horizontal axis is the number of levels of channel quantization. Because everything is discrete, even if you have like a binary input AWGN channel, you still have to quantize it. So this is just the number of levels of quantization for the channel. The vertical axis is the noise threshold. And so higher, in this case, higher is better. At the top is the AWGN noise threshold for a 3/6 regular code. And then the red curve is, again, unquantized messages, but for the quantized channel. So what you see here, the first curve is if we have k is equal to 2, that's 1 bit per message for the message LDPC decoder message quantization, and that performs quite poorly. But if we go up to k is equal to 4, that's 2 bits per message. We get a big jump in the noise thresholds. And then you can see if we get all the way to 4 bits per message, then we're getting really quite close. We're getting quite close to the noise threshold for the unquantized case. All right, so that was fine for infinite length. What about finite length? Well, fortunately, we got similar results. So, for example, this is for a rate 0.56 code of block length 4000, showing E beyond N naught versus the bit error rate. The black curve is floating point, and the green curve is 4 bits per message. So that's quite close to it's quite close to the floating point. So that was quite satisfying. And then the blue curve is 3 bits per message. So indeed, you can see that there's a little bit of a gap, but not too bad, not too bad. I'll skip this. So the most recent work was that this was implemented in an FPGA. So FPGAs can also implement the lookup tables. And in this case, the student found something very interesting about getting the symmetry out of the lookup table. And indeed, so the state of the art in this case was offset min sum algorithm. And so what we found was that in the 4-bit case, the Max-Let method has lower error rates than state of the art min sum. So I believe that's moving from the purple curve to the purple curve to the blue curve. And then at 3 bits, the Max-Let has a higher throughput per unit area ratio than the offset min sum. I mean, in fairness in advertising, it really represents a trade-off, and it really represents a trade-off in the performance complexity, but it does look a very positive result. Okay, so let's wrap up. So I tried to show some overlap between machine learning and information theory and how these ideas are related to each other, particularly when designing these quantizers. So the Max-Let method worked really well for LDPC decoders. And essentially what we did was optimizing non-uniform quantization methods for use in VLSI hardware. So there's lots of open questions. The one that I really want to know is, can these techniques be provided more generally, for example, to equalization and detection? And what about other decoders? For example, non-binary LDPC codes or dipolar codes and so forth. And so in this case, we assumed that we always knew what the channel distribution was, but of course, in general, we don't know what channel distributions are. So how could we deal with that? And then this other thing is like, why is 4 bits per message so special? It's kind of, I don't know, it's the result of a numerical experiment, but it's very curious to me why it's 3, not 3 and not 5, and if 4 bits per message is good enough. Okay, great. I'm done. Thank you for your attention.
So, are there any questions or comments?
No. In the BP, we have the 3 types of message, error message, and variable to check and check variable. Do we need to use the same quantization level for them, or can we use different quantization level for each of them?
Yeah, basically, we are using different quantization levels at every step. Maybe I called this operation quantization. Maybe it's a little bit misleading, but it's really what we're doing is designing lookup tables at each step. And so it's not even quantization per se. We're mapping from one discrete alphabet to another discrete alphabet.
Yeah. But input of LUT is one kind of message.
Yeah.
And output is one kind of message. So maybe the number of quantization levels is a very important hyperparameter.
Okay.
So for my feeling, it is fairly difficult to choose the hyperparameter before constructing the LUT. So how to think about?
Right. Okay. Yeah. Now I understand your question better. Yep. Yeah. Okay. In one sense, the hyperparameter is just one. It's the number of bits, and it's either 2, 3, 4, or 5. Basically, it's a very small choice. Very small choice of numbers. One question would be how to quantize the trade-off of the channel versus these messages. And another question, I never saw anybody ask, but you could actually, the number of variable bits could be different than the number of check message bits. I never saw anybody study that. The intuition should be that check doesn't require so many bits, but I didn't see a paper on that. Yeah.
Okay.
Any other question? Actually, I'm interested in your second open question about the non-binary as well.
Oh, okay.
You tell me the difficulty of applying your method to this non-binary code.
Yeah, so actually, honestly speaking, I currently have a student working on this, and he's just getting started. But the answer is that as the alphabet, if you just did it naively, the alphabet size becomes a problem very quickly. Okay, so there was one paper where they did non-binary LDPC coders using this technique, and they stopped at GF4. They had GF3 and GF4, and nothing bigger because of complexity issues. So what we're finding right now is that if you are not naive, if you pay attention to the structure of the finite field, then probably we can have a lookup table which is much smaller. Yeah. So I think the answer is yes. It can be good. Yeah.
How does binary work?
Yeah, within the past few months, I saw a paper on this. So I think, yeah, you have a belief propagation representation of a polar code, right? And so it should be quite natural to apply this technique to the polar code graph, I think.
Thank you. Curious about the relation between the application of information problem. So the information bottleneck problem, you try to maximize the end-to-end information. That's another way of writing it, but kind of setting a constraint on the bottleneck information. Now, in the information bottleneck formulation, you don't have a constraint on the alphabet of C. So in your case, so the alphabet of Z is the same as the alphabet of Y. So I'm just wondering if you actually tested the information bottleneck problem.
So, yeah, your comment that the information bottleneck doesn't have a constraint on Z is interesting to me because I never paid attention to that. Because when I ran the information bottleneck method, I just, I set Z to be equal to what I wanted.
And that's still not. Even when you set, so when you set Z in the information bottleneck problem, the similar to the technical problem,
they are the same. I mean, yeah. Yeah, basically the information bottleneck, it has this, one of the steps, it looks like, it's kind of like the what do they call it, soft max or something, where you have like, ratio of two numbers with beta in both of them. And as beta gets big, basically it becomes a selection selection function. The softmax becomes hardmax as beta goes to infinity. So, yeah, I assume from what you said was that if I just ran the information bottleneck for some problem and I chose Z to be big, it wouldn't affect the outcome of the result. Yeah, but even like this one, right? You need to know what Z is. So if you told me you're using Z with a big alphabet.
I think that we can result from the cardinality. I think that's how observability variables in the cardinality. I think the cardinality applied is the often.
Oh, yeah, that wouldn't surprise me because, you know, as I mentioned before, right? Where'd that go? Yeah, when Z is bigger than Y, the problem is trivial.
The maximization of each information is trivial, but the problem becomes different.
Yeah, I think you must be right because when beta goes to infinity, this is a discrete mapping, right? It's not probabilistic, deterministic mapping. But when beta is finite, then these become probabilistic. So yeah, in the information bottleneck case, that would be more interesting. Yeah, I'd be interested to know about that paper. Yeah, I cheated. Yeah, I don't know that specific one. I mean, of course, there's two ways to answer that question. Yeah, I mean, of course, there's been work on basically, this kind of looks like a neural network, right? And so some people said, yeah, let's decode this using a neural network. And in some cases, they can get good results for certain types of codes, even if they're not necessarily sparse. The problem that I was interested in, and we spent some time looking at it, was to build a neural network using discrete variables. And so in that case, you know, you'd want to optimize this mapping based upon some output way over here. Yeah. And that just, I mean, it just looked crazy complicated. Like we couldn't even find a simple case that was tractable. But that doesn't mean it's not possible. I think it would be really interesting to solve this problem. So I think that's an interesting open problem.
So I have a question on this educative method.
Yeah.
My question is, you formulate the design program with the factor graph, but the factor graph is a top fiber. Graph is not hard. So you can't use some method for But why, could you tell me the details of what
I'm sorry, I didn't quite catch. Let me change to that slide. Oops.
Factor graph is not the end, not fast as this is that so you can run the factor algorithm.
If the graph is not sparse.
Yeah.
Yeah, kind of the assumption is that you already have a factor graph which works well in floating point. So if you already have a factor graph which works well for floating point, then let's try to implement discrete version. But I don't think we can help. This method won't help if the floating point version works poorly.
So you find the MDT code with factor graph.
No, I don't have a dense factor graph.
Yeah, and everything is coded for the
Right.
And you combine the cluster with interactive design, and the method. So, overall graph is one.
I don't have a dense graph. Why do you say I have a dense graph?
Yeah, I think the speed propagation does work for dense graph.
Yeah, basically,
Yeah.
basically no. Yeah. Yeah, in these results, we only have sparse graphs.
Any other questions?
One question. Your open question, the last one, I also, I'm interested in, what is special about orbit? If you have any intuitive opinion, I'd like to hear about that.
Yeah, I really don't know. I really don't know. Why is it like that?
So, now the neural network world, they're so interested in compensation of the message of neural network. And they try to find, for example, values, three variable message. And from these results, 4-bit is a little bit higher than the such a trend. So, do you think it's a limitation of the BP?
Maybe not, right? Because in the neural networks, they have a lot of it's many connections, right? And so maybe even if some connections have a lot of quantization error, they can have some kind of redundancy in the graph. But these LDPC graphs don't have so much redundancy. So maybe if you did make a redundant LDPC code graph, just add some linearly dependent rows or something, maybe the number of bits would go down. And I think the guys in industry, right? They said sometimes they actually prefer graph LDPC codes that have column weight 4 rather than 3 because it works better under quantization. So yeah, could be. Yeah, I think maybe it's problem dependent. Depends upon the problem.
Thank you.
Yeah.
Okay, so let's start the speakers.